In this video, we'll be talking about infinite limits. Those are the limits such that the limit as x approaches infinity of some function. It's important to note that there's only so many facts about infinite limits that we can actually comprehend and deal with. The most basic concept is the limit as x goes to infinity of 1 over x is going to be equal to 0. The best way to understand this is to think about having a single pizza, and then you're going to have a certain number of friends over to help you eat that pizza. As you increase the number of friends you invite to eat that pizza, you'll notice that the amount of pizza every individual gets is going to continue to get smaller and smaller. 1 out of 10, 1 divided by 100, 1 pizza divided by 1,000. Eventually you get to the point where I'm dividing 1 by so many friends that no one's going to get any pizza whatsoever. You'll get a crumb, or nothing at all. So this is the most basic concept of an infinite limit. There are two additional properties that we can try and comprehend and identify. The first one is an amalgamation or a manipulation of this one, such that if I have a constant in the numerator, a constant, not something going to a constant, but an actual number, divided by x to the power of n, such that that n is a positive number, so greater than 0. If this is the case, this is then also going to be equal to 0, because we're still taking a certain number of pizzas, but we're dividing it by a certain number of friends, such that that certain number of friends is going off to infinity. So this value is getting larger and larger, and this value is remaining the same. So that is the most basic first type of limit, and then you've got the more complicated version. This is also true if you talk about the limit as x approaches negative infinity. So it's a little bit more difficult to comprehend, but the concept is still the same. The value in the denominator is getting so large that 1 divided by a number so large, it's going to approach 0. And again, that also applies to the constant in the numerator divided by x to the n. That is also going to go to 0. So there's one more limit rule in terms of infinite limits that we want to identify, and that's the limit as x goes to infinity or negative infinity of the value simply x. This right here, if there is nothing else with it, will be equal to the value of infinity. In some cases, some people might refer to this as a DNE limit, or a does not exist. And I would disagree and say that the limit exists. It doesn't go to a value, but it does tend towards infinity, meaning it's going to tend towards a value so large we can't comprehend, or it's simply going to increase without bound. So these are the most basic limits that we know in terms of infinite limits, and these are actually the only ones we can really apply. All of the other rules that we've learned utilizing limits doesn't actually work. So plugging the infinity in doesn't actually work, because 1 over infinity isn't a number. It doesn't make mathematical sense. But as the limit of x approaching infinity, that means this x value is approaching infinity, I get 1 divided by a number extremely large. So the argument here is that these are the only limit values that we can actually apply. Factoring won't work, conjugate won't work, common denominators won't work. So when we look at our first example, the limit as x approaches infinity of 2x squared plus 5 divided by 3x squared plus 1. The method that we're actually going to utilize is a very specific method in order to get every single individual term here, every term, to be in the form of something that looks like this. So what we're going to do to make that happen is I'm going to look to the largest power in the denominator. That's this x squared. That is the largest power in the denominator. I will then take everything on top and on bottom, and I will multiply it by 1 over that largest power of x in the denominator. So again, we're looking to the 3x squared, that's the largest power of x, that's the leading term in the denominator. I'm going to multiply by 1 over x squared. I will then take this and I will distribute it into all of these pieces. Again, this is mathematically fine because I'm multiplying by nothing more than 1. So this is now the limit as x goes to infinity of, and very carefully, 2x squared times 1 over x squared becomes 2x squared over x squared. 1 over x squared times 5 becomes plus 5 over x squared. This is all divided by 1 over x squared multiplied by 3x squared becomes 3, and 1 over x squared times 1 is 1 over x squared. Now you'll notice in this case right here I actually simplified it. And that's what I'm going to do up here as well. I just didn't want to do it too quickly. So the limit as x goes to infinity, the x squareds will cancel out, leaving me with 2 plus 5 over x squared divided by 3 plus 1 over x squared. And now we can actually apply the concept of as x approaches infinity, I will separate this limit to all of the pieces. Assuming all of the individual pieces exist, I am allowed to look at the limit this way. And in most cases, we should be perfectly fine by separating this limit over all of these terms, additions, multiplications, and or divisions. Now, what's important to note is that this only works if they all exist. But as x goes to infinity of 2, we get the value of 2. As x goes to infinity of 5 over x squared, we get a constant divided by something going to infinity, so plus 0. Divided by, as x goes to infinity of 3, we get 3, and as x goes to infinity of 1 over x squared, we get 0. And therefore, we get the limit is equal to a value of 2/3. So this is the method that we're going to apply for every infinite limit. We will look to the denominator and find the largest exponential value in the denominator. So in this case, it's x to the power of 2. I'm going to multiply top and bottom by 1 divided by x to the power of 2. I will manipulate this algebraically, and then again, this step right here doesn't need to be written, but it's what we're actually doing. We're attempting to evaluate the limit as x goes to infinity of this term, and then this term, and then this term, and then this term, and then we're going to go ahead and add these two terms on top, divide it by the two terms on the bottom, and end up with 2/3.